Hello students, welcome to 60 out of 60 in KCET Chemistry 2025 series in just 200 days. So yes, as you all know, we have started a series where we are going to cover every concept of chemistry and we are going to solve a lot of PYQs and practice many questions, right? So that you can hit that perfect 60 score in your KCET 2025 chemistry examination. So yes, in today's video, I will be covering the part 2 of chemical kinetics, where we will be doing topics of effect of temperature, effect of catalyst and collision theory. Okay, so we have already completed solutions chapter, electrochemistry chapter and chemical kinetics part 1. Okay, so today we are doing chemical kinetics part 2 and with this we are going to complete this chapter also. Okay, so holistically we'll be doing all this, like chapter will be completed. So yes, now any questions can be asked from this. I hope you will be able to do it after completing this video. Okay, so now one more important thing, please do not forget to join our WhatsApp channel, because the notes and the questions, the solutions, everything will be provided in our WhatsApp channel, and the link of the WhatsApp channel will be there in the description section of this video. So simply you have to go to the description section of this video and click on the link and join the channel so that you do not miss out on any of these important things. Okay, fine. So now let's get started. I hope everyone is ready with a notebook and a pen, and note down all the important formulas and important concepts, and let us practice some questions as well as PYQs. Okay, so yes, I hope all my children are ready. Let's get started. So first, coming here, we will discuss, that is how am I going to cover this chemical kinetics lesson. I have already discussed in part 1. I'll tell you again. So I have basically divided the chapter in two parts, that is part 1 and part 2. So in the first part, I'll be covering your rate. I have already covered, that is rate of reaction. Okay, next we have covered factors affecting the rate of reaction. Then we have covered effect of concentration. This is very, very important. And next we have covered the methods to determine the order of a reaction, right? And here we have discussed 4 methods and we have already given you examples of these all methods. So if you haven't understood any of these concepts, please watch the part 1 and then come to part 2. Okay. Now in today's video, that is part 2, we are going to cover the next part, that is first one, effect of temperature, very important. In 2024, 3 questions were asked from chemical kinetics and 2 of them were from effect of temperature. Okay, so very important concept. Next, coming to effect of catalyst. This is also very small topic but very important one from the exam point of view. And the next one is collision theory. Okay, fine. Now coming to starting the first one, that is weightage year wise. Okay, so if you have already discussed in part 1, so I will not take much time here. So if you see, we can expect around 3 to 4 questions from this chapter every year. Okay, 3 to 4 questions we can expect from this chapter every year. Okay, now coming to the next one, that is chemical kinetics part 2, today's topic, that is effect of temperature, effect of catalyst, collision theory. Then in effect of temperature, I will be covering 2 important topics, that is Arrhenius equation and that is Boltzmann distribution curve. Okay, these 2 topics we will be covering for in effect of temperature. Then we will go to effect of catalyst and then we will go to collision theory. Okay, now coming to the first important topic of today, that is effect of temperature. Very, very important concept, students. Please be very careful while understanding these concepts. See, for a chemical reaction with a rise in temperature of by 10 degree. So that means when you increase the temperature by 10 degrees Celsius, suppose you are doing a reaction at 17 degree and then you are doing the reaction of 27 degrees Celsius. Okay, so for example, at 17 degrees Celsius you did a reaction, the rate constant is K1, and at 27 degrees Celsius if you do the same reaction, the rate will be almost equal to twice of K1. Okay, so that is what it is observed, that for a chemical reaction with a rise in temperature by 10 degree, the rate constant is nearly doubled. Okay, so the rate constant becomes double. Clear? So now coming to the next one, that is Arrhenius equation. What is this equation? So see, very simple, like for understanding the effect of concentration on rate, we had rate law, one rate law expression we had, which tells you the relation between the rate and the concentration. Similarly, we have an equation which tells the relation between rate and temperature, rate constant and temperature. Okay, that equation is nothing but your Arrhenius equation, named after the scientist Arrhenius. Clear? So what is the use of this equation? See, The temperature dependence of the rate of a chemical reaction can be accurately explained by Arrhenius equation. So what is simple words what I will say? Arrhenius equation tells us the relation between temperature and rate constant. Okay. Now if I see the formula for this one, that is K is equal to A into e to the power of minus EA by RT. Okay, now I will tell you all the terms here, do not worry. So K, I think all of you will be knowing, that is rate constant. Okay, rate constant. Next, what is A? A is called as Arrhenius factor. Okay, Arrhenius factor, or we can also call it as pre-exponential factor. Okay, pre-exponential factor. Okay, next I have EA. So EA is activation energy. I'll tell you what is activation energy. All these terms we will discuss in detail. So just now we'll write this one. And R is our gas constant. R is gas constant. Okay, and its value is, you can take 8.314. Okay, next coming to T. T is temperature. Okay, and temperature has to be in Kelvin. Clear? So these are the different factors, these are the different terms, this is the equation. So you can see how it is relating rate. This rate constant can be related to rate, and dependency of rate and temperature. Rate and temperature we can get through this equation. Okay. Now coming to the next one, this graph. Here we will be understanding all these terms whatever I have told you. See. Now one second. Okay. Now see, there are suppose two reactants H2 and I2. Okay, they are reacting to give you HI. H2 and I2 is reacting, two reactants are reacting to give you a product HI. Now what happens, this line, this part you can see. Okay, so this is the energy of the reactants. H2 and I2 energy is this one. Okay, now this one, this is the, there is something called as activated complex. Now what is this activated complex? See, every reactant cannot directly convert into product. They need to go through a transition state, after which they will get converted to product. So that transition, that like reactants have, so just imagine like this, for every reactant, okay, I'll write here, every reactant has to go to one phase. Okay, let anything, after that only it will be converted to products. Now this reactant has to convert it to something, that something is called as your activated complex. Okay, so no reactant directly gets converted into product, they first get converted to activated complex. This activated complex gets converted to products. Okay, so now this energy of the activated complex is this one. Okay, you can see. Okay, so this is the energy of the activated complex, this one, right? Now, so reactant's energy is this one, activated complex is this one. So we have to give some energy to the reactants to reach this much level, right? The energy level from the reactants level to the activated complex energy level, you need to give some energy. So that energy what you need to provide to the reactants so that they can reach, or so that they can get converted to activated complex, that energy is called as activation energy. I hope everyone is getting. See, reactant cannot directly convert into products. Reactant has to convert into something called as activated complex. From activated complex, they will get converted to products. Now, reactant has a certain level of energy, activated complex has a certain level of energy. Now, the reactants must gain, like when reactants will get that energy, they will get converted to activated complex. So, this amount of energy that must be given to the reactants so that they can get converted into activated complex is called as your activated energy. Okay. Now this activated complex now gets converted to products, that is 2HI. So now this was the energy of the reactants and this is the energy of the products, right? So this is the energy of the products and this is the energy of the reactants, right? Now this difference, energy of reactants and products, is called as your delta H, or energy of the reaction. Getting? So we can get this one, activated energy clear, activated complex clear. Okay. So this activation energy is taken here in this equation. Okay, fine. Now let us go to the next part. Okay, now if I take So that equation was K is equal to A into e to the power of minus EA by RT. Now if I take ln on both sides, ln on both sides, then I will get ln K is equal to ln A minus EA by RT. Now this graph, this equation can be drawn into a graph, okay. So now you can see this is a straight line equation. I can write it in the form of y is equal to, this is m, x and this is c. X is what? 1 by t, okay. Y is ln K, c is the y intercept and slope is minus EA, right. So you can see this graph here I have drawn for 1 by t versus ln K, okay. 1 by t versus ln K graph you can see. Here the y intercept is ln A, this is y intercept, and the slope of this graph is negative slope and the slope value is minus EA by R, okay, and x is your 1 by t. So we will get this type of graph for Arrhenius equation, a negative slope. Okay. Now what happens, suppose we just see now that for every 10 degree rise the temperature becomes twice, right. The temperature, for every 10 degree rise in the temperature the rate constant becomes double. Now suppose that we are not making double, we are suppose changing by 30 degree, 40 degree, 50 degree, then how the rate constant will change. So for that we need a formula, and that formula is given here. Log K2 by K1 is equal to EA by 2.303 R into 1 by T1 minus 1 by T2. So now what is this one? See, K2 is the rate constant at temperature T2. K1 is the rate constant at temperature T1. EA is what we have already discussed, that is activation energy. Next, R is gas constant, okay. R is gas constant, and then T1 is first temperature and that is lower temperature, low temperature, and T2 is the increased temperature. So I can write the high temperature, okay. So from this, if two temperatures are given, so suppose now T1 is given to you, T2 is given to you, and you know that at T1 the rate constant is K1, then what will be the rate constant at T2? If it is if we need to calculate, then we can use this formula. Or else if K2, K1, T1, T2 is given, you need to calculate activation energy, that also you can do. Or else if K2, K1 is given, T1 is given, T2 is asked, right. So any four, like any variable, so we have 1, 2, 3, 4, 5 variables are there. Any 4 will be given and 1 will be asked. If you want to calculate, you can use this equation. So this is Arrhenius equation at two different temperatures, okay. Okay, now coming to what is this Boltzmann curve, okay. So Boltzmann curve we'll understand, just two diagrams we need to understand. See, so what happens, as I told you, every reactant must possess a certain amount of energy to get converted into products. When the reactants possess that certain amount of energy, we call them activated complex, right. So to that energy required to convert a reactant to an activated complex is called as your activation energy, right. So now what happens, we cannot measure the energy for each and every molecule and do, right. So for that Boltzmann did a graph where they showed fraction of molecules and kinetic energy they plotted, okay. And see, now what it is saying, see, this is the kinetic energy is increasing, okay. So this is some energy which most of the particles are having this amount of energy, that is the most probable kinetic energy. Now very less particles, so this energy is less, okay. So I can say that very less fraction of particles are having this less amount of energy, and also this is high energy, okay. Very less amount of particles are having high energy. There are some medium value of moderate kind, there is some medium value where most of the particles have the energy, okay. Most particles have, so now you see, suppose this is a low energy, okay, and this side high energy, and this is medium energy. Just imagine like this. So what they are saying that some very few particles have low energy, very few particles have high energy. There is a maximum number of particles which has the moderate energy, and that energy we call as most probable kinetic energy, okay. That is most probable means many molecules possess that amount of energy. But for reacting, for becoming that activated complex, this much energy is not enough. We need high energy, we need particles in the high energy region which can get converted into products, okay. Getting this one, let me explain you again. There are some particles which has very low energy, there are some particles which has very high energy, and there is a majority of particles which has a medium value of energy, and that is called as most probable kinetic energy. Now what happens here? The particles which have high energy, they can only get converted into products. Okay, so now what happens when you increase the temperature? Okay, so now here I have increased the temperature. Okay, now when you increase the temperature, what you can see the changes in the graph. See, this graph, first one is for T, temperature T, and the lower graph is for T plus 10. Now see, this line is activation energy. Okay, so these particles which have energy greater than or equal to activation energy can form products. Okay, so I can say that these particles can form products, the particles in this region. Why? Because they have energy, greater than or equal to activation energy. Okay, so now what happens? Earlier when temperature was T, these many particles were there with that much energy. Okay, now when you increase the temperature, number of particles having energy greater than the activation energy or equal to activation energy increases. Number of particles having energy greater than or equal to activation energy increases on increasing the temperature. So now more number of molecules can form products, right? If more number of molecules will form products, the rate will increase. If rate will increase, rate constant will increase, right? So that is why the K value will increase. Okay, so what is here? This area shows the fraction of additional molecules which react at 10 plus 10 degrees. So earlier what happened? So if I clear it again, see once again. Now see, this black region is the number of particles that can form products at temperature T. When you increase the temperature to T plus 10, this grey color shadow, these many particles got added extra, right? So now if you see at T plus 10, these many particles total, at T plus 10, the total number of particles can form products, right? So if these many particles can form products, more number of particles can form products, then definitely rate constant will increase. So that is why when temperature increases, rate constant increases. What will you say the reason for this? When temperature increases, the number of particles possessing energy greater than or equal to activation energy increases, and that is why the rate constant increases. Okay, fine. Now let us go to the next one to understand effect of catalyst. So first of all, what is a catalyst? Let us understand. So a catalyst is a substance which increases the rate of the reaction without itself undergoing any permanent chemical change. So catalyst is something which can change the reaction, which can increase the rate of the reaction, but itself it will not get changed. Okay, suppose you add H plus as a catalyst. After the reaction again you can find H plus. Okay, H plus or the catalyst will not get consumed in the reaction. Okay, now catalyst, how does it do that? What is the mechanism of catalyst working? So catalyst provides an alternative pathway of reaction mechanism by reducing the activation energy between the reactants and products, and hence lowering the potential energy barrier, hence the rate of the reaction increases. So now if I tell, there are different reasons. If I say, just ask you, tell me how temperature increases the rate of the reaction. How? So this is a question for you. Okay, how temperature increases the rate of the reaction? I want everybody to answer this question. How temperature increases the rate of the reaction? What does happen when the temperature increases so that the rate of the reaction increases? This is what I just discussed now, right? I want everyone to answer this in the comment section, how temperature increases the rate of a reaction. Now coming to catalyst, how catalyst will increase? How catalyst increases the rate of reaction? How catalyst increases the rate of reaction? So this is by providing an alternating pathway of low activation energy. By providing an alternative pathway of low activation energy. Now just let me give you an example. Suppose your home is here, okay, home is here and your school is here. Okay, every time how you used to go, you here some suppose I'll tell here some river stream is there, okay, river stream is there, so you used to go in this way every day, okay. Distance you need to cover was from here to here. Now one day one catalyst came, okay. Catalyst is something which can carry you in this case, okay. They can, like you can example a boat is a catalyst here, okay. So what can boat do? Boat can carry you, okay, and can go through this one this way, right, and can increase the speed or increase the speed by which you can reach the reaction, you can reach the school, right. The time consumed will be less, right. So now what happens here? Because of this catalyst, it is providing you a different way. It is not going through this way. It is providing you a different mechanism by which you can reach the school in a much faster way, right. Similarly, catalysts also do the same thing. They provide a new mechanism, they provide a new method of the reaction by which the rate of the reaction that is by which the activation energy decreases. Now how activation energy is affecting the rate of the reaction, that we will discuss. So now see, when if you have remembered this Arrhenius equation, it was K equal to A to the power of minus EA by RT. So I can write like this 1 by one second, I can write like this 1 by e to the power of EA by RT, right. Now what happens when catalyst is used? When catalyst is used, what does it do? It is providing a new mechanism with lower activation energy. So when catalyst is used, activation energy decreases. Now see, if activation energy will decrease, this whole term will decrease. That means e to the power of something will decrease. If e to the power of something will decrease, then k will increase, inversely proportional. You are using catalyst. Catalyst is providing you a new method in which the activation energy is low. If activation energy is low, this numerator part is low, that means this fraction will become a low value. E to the power of something, this whole value will decrease. If this whole value is decreasing, then k value will increase, right. Rate constant will increase, and as a result of which the rate of the reaction also increases. I hope it is clear. 3 points. What happens when we use a catalyst? When we use a catalyst, it provides an alternative pathway, a new route it provides for the reaction. Now this route has a lower activation energy than the original method. Now if there is a low activation energy, then this fraction value will decrease, e to the power of something, that value will decrease, and k value will increase, right. Okay. So now next, but this is important, a catalyst does not alter the Gibbs energy and the equilibrium constant, okay. These two things will still remain the same. The only thing is the reaction will be completed faster, okay. At a less time you can get the reaction completed, okay. Now we will see a graph for this one, okay. Now you can see here this one, the first one, the one which is solid line, okay. So that graph activation energy, you see what is the activation energy, reactant energy and the activated complex. So this is the activation energy for without catalyst. When we use catalyst, it is providing a different mechanism such that its activation energy decreases. The reaction activation energy is decreasing, right. This much decrease has happened in the activation energy. As I told you, when activation energy will decrease, right, the fraction value will, e to the power of that fraction value will decrease, as a result of which k will increase, okay. Fine. Now let us go to our question, okay. So let's solve some important questions and practice them. So an endothermic reaction A to B has an activation energy of 15 kilocalorie per mole and the heat of the reaction is 5 kilocalorie per mole. The activation of the reaction from B to A is, okay. Now first let me tell you how the graph of an endothermic and exothermic looks. So in endothermic what happens, remember, okay, product energy will be more than the reactant energy. So if I draw a endothermic graph, it has to be like this. If this is reactant energy, product energy should be more than reactant energy. Now in case of exothermic, you should remember, in case of exothermic, product energy will be less than reactant energy, okay. So if I draw a graph like this, if this is reactant energy, this has to be product energy. Please remember this thing. For exothermic graph will be like this, for endothermic graph will be like this. Now I'll erase this exothermic part so that we can do our question, okay. But you note down these two things, sorry, okay. Yeah, now see, we have drawn an endothermic reaction A to B. So I have written R and P, I will make it A to B. Okay, this is A and this is B. Okay, next. Has an activation energy of 15 kilocalorie per mole. So activation energy means what? Energy of the reactant to the energy of the product. So this value is how much? 15 kilocalorie per mole. And the heat of the reaction is 5 kilocalorie per mole. Heat of the reaction means energy of the products minus energy of the reactants. So this is the energy of products, this is the energy of the reactants. So this gap, okay, this gap is called as 5 kilocalorie per mole. This is 15, this is 5. Now the activation of the reaction from B to A. So if I see B to A, B energy is here, right? So this is the activation energy from B to A. So now what is this value? This total is 15, this is 5, then this value will be 10 kilocalories, right? So the activation energy from B to A is your 10 kilocalories per mole. Correct answer for this question is option number C. Okay, I hope all are getting this. Once more we can discuss. A to B, reaction is going like this, endothermic graph. Activation energy is from the energy of the reactants to the tip point. So this one is your activation energy for A to B. Now heat of the reaction is energy of the products minus reactants. So this value is 5 kilocalorie per mole. Now the difference between this one 15 and 5, that is 10. So this BA graph, if I want to see B to A. So this is your activation energy for the backward reaction. Getting? Okay. So now let's solve the second question. The rate of a reaction gets double when the temperature changes from 7 to 17 degrees Celsius. By what factor will it change for the temperature change from 17 to 27? So if you see 17 to 27 is also a rise of 10 degree. So here also the rate will get by doubled, or you can say 2 times it will increase. So the correct answer for this question will be option number C. Right, very simple, without any solving we can do it. Okay, now let us see the next question. The velocity constant of a reaction at 290 Kelvin was found to be 3.2 into 10 to the power of minus 3 second inverse. So at 290 Kelvin, what was the rate constant? I can write 3.2 into 10 to the power of minus 3 second inverse. Now when the temperature is raised to 310 Kelvin, so when the temperature is raised to 310 Kelvin, what will be the rate constant? Again see, 290 if I increase by 10 degree, it will become 300, right? So into 2 if I do double, because for every 10 degree it becomes double. So I can write 6.4 into 10 to the power of minus 3. Now again from 300 to 310 if I do, it will get double. So I'll get 12.8 into 10 to the power of minus 3. So we can write it as 1.28 into 10 to the power of minus 2. So the correct answer for this question will be option number D. Okay, so how simply we can solve these questions? Just you need to remember that for every 10 degree there is an increase of the rate constant becomes double. Okay, fine. So now coming to the next important I can say the concept, that is collision theory. Okay, so what does collision theory say? See, according to this theory, the reactant molecules are assumed to be hard spheres. The reactants are your hard spheres, and the reaction is postulated to occur when these molecules collide with each other. So reactants are your spherical shape hard spheres, and when they collide with each other, the reaction happens. Okay, so this is what collision theory tells us. Now there is one important definition here. The number of collisions per second per unit volume of the reaction mixture is known as collision frequency. So what is collision frequency? The number of reactions, the number of collisions that takes place in 1 second and in 1 unit of volume. Like for example, if you have taken a container, see, okay, and here there are 2 reactants. This is 1 unit of volume, this is second unit of volume, this is like these are all 1 unit of volume. So in this particular 1 unit of volume in 1 second, how many collisions are taking place? That is called as your collision frequency, and it is represented by the letter Z. Okay, next, and another factor which affects the rate of the reaction. First factor is collision. Okay, another factor which affects the chemical reaction is your activation energy. So how does this affect? If activation energy is low, then rate of the reaction is fast, right? Inversely proportional. Just now we have seen in the graph, right? In the equation, Arrhenius equation also, if activation energy is low, then rate constant will be more, or rate of the reaction will be high. Okay, so now what happens? Based on this collision theory, there was a equation given for rate constant. Rate is equal to ZAB into e to the power of EA by RT. This ZAB is written in this way. Okay, what is ZAB? ZAB is the collision frequency between A and B. Okay, how many times A and B have collided per second per unit volume, that is ZAB. Next, EA is your activation energy, R is gas constant, T is temperature. So this is how, according to collision theory, the rate of a reaction was expressed earlier. Now after that what happens? Now see, now they said that again it was observed that if every time it is colliding, it doesn't form products on every collision. If for collision also there has to be a certain condition. Okay, what is that condition? See, first of all, what collision theory says, reactants are hard spheres and when they collide with each other, products are formed. The second thing that comes, that every collision does not lead to product formation. There is some condition regarding the collision also. So what is that? Now see, the collisions in which the molecules collide with sufficient kinetic energy, the collision should also have sufficient kinetic energy. It's not that slowly they are coming and colliding, product will form, not like that. They should collide with a sufficient kinetic energy, and this sufficient kinetic energy is called as your threshold energy. And this is very important, proper orientation. They should collide with proper orientation, in proper direction. Okay, not only with collision which should have proper energy, but should also have proper orientation, so as to facilitate the breaking of bonds between the reacting species and formation of new bonds to form products are called as effective collisions. So now we discuss first collision theory says that yes, reactants are hard spheres and when they collide the product will form. But after that they modified it, say that reactants should not only collide, rather they should undergo effective collision. Now under this effective collision there are two parameters. First is the energy parameter, which says that the reactants must collide with a sufficient amount of kinetic energy, and the second factor that tells is the reactants must collide in a proper orientation. Okay, so now if we see here, now see, to account for this effective collisions, another factor P called the probability or steric factor is introduced. I'll explain this after some time. Let us see now. See this graph, this diagram you can see here. What does it say? CH3Br plus OH minus gives CH3OH plus Br minus. Now OH minus has to collide with this particular reactant. Okay. Now OH minus can collide in this direction, can collide from backwards also. There are two orientations in which the OH can collide. But if the OH collides from the front side, okay, if the OH collides from the front side, then there will be no product formation because the orientation is wrong. So for product formation, the OH must collide from the backward side, right? So then only product will form. So if CH3 is like this and OH is coming from this way and bromine is here, OH is coming in this way, then in that type of collision, that there is no product formation. We cannot say that this collision is an effective collision. For effective collision, energy should be sufficient and orientation should be correct. So for product formation, OH must collide from the backward side, right? So that is what they are saying, that there are two factors of effective collision. One is sufficient energy and another one is your proper orientation. So for sufficient energy, we have the factor ZAB e to the power of EA by RT, but which there should be something which tells us about the orientation or the factor about the orientation. So for that we have a new factor that is called as P. So now the collision theory gives a new equation, rate is equal to P dot ZAB into e to the power of EA by RT. Now here I will be telling you the different terms here. Okay, so now see, what is P? P is your probability factor, okay, or steric factor. Okay, it tells about the orientation of the molecules. Now what is Z here? ZAB is collision frequency. Now this term is very, very important, which tells about the energy, tells about the number of particles having energy greater than or equal to activation energy. Okay, number of particles, or I can say fraction of molecules. Fraction of molecules having energy greater than or equal to activation energy. So now earlier the collision theory said that rate is equal to Z into e to the power of EA by RT. There they did not consider about this orientation factor. after modifying that, understanding the orientation factor, another constant was multiplied, that is P. Now what happens, this P and ZAB is taken as A in your Arrhenius equation, modified version of Arrhenius equation. Okay, so this is, you can say, the initial form of Arrhenius equation, and then it was modified and finally we got the Arrhenius equation. Okay, so that is very simple about collision theory. You have to remember, reactants are hard spheres. They should undergo effective collisions. Under effective collisions, there are two parameters. One is they should have sufficient energy, another is they should have proper orientation while colliding. Okay, fine. I hope you are getting. Now let's do some practice questions. Okay, so before that, I'll tell you, I have given you this question as a homework in the part 1 of chemical kinetics. So let us see its solution. So this was your homework question, right? Okay, in a first order reaction, the concentration of the reactant is reduced to 12.5% in 1 hour. When was it half completed? Okay, see, now 100% was initial, then it will become 50% in T half, right? First order means in another T half it will become 25%, and then in another T half it will become 12.5%. Now what happens? They say that it converts to 12.5% in 60 minutes, right? 60 minutes, so every half-life is same, so I can say this is 20 minutes, this is 20 minutes, and this is 20 minutes. So when was it half completed? It was half completed in the first 20 minutes. The correct answer for this question is option number A, that is 20 minutes. Okay, now coming to test yourself, second question. Here I have given you a hint also. A first order reaction is half completed in 45 minutes. How long it need for 99.9% of the reaction to be completed? So I have told you that T 99.9%, okay, is equal to 10 times of T 50%. Okay, so now I can say that T 99.9% is equal to 10 times of what is T 50%? 45 minutes. Okay, so I can say that is 450 minutes. Okay, so now I need to convert into hours because the options are in hours. So divide by 60 if I do, for converting into hours, I'll get 7.5 hours. Okay, the correct answer for this question will be option number D. Okay, fine. Now let us do previous year questions from today's concept that we have discussed, that is effect of temperature, effect of catalyst, and collision theory. See the first question. The rate constant K1 and K2 for two different reactions are given respectively. The temperature at which K1 is equal to K2. Okay, so let us see here that they are telling at what temperature K1 will be equal to K2. Okay, so first let us write what is the value of K1. K1 is 10 to the power of 15, okay, into e to the power of minus 1000 by T. Now K2 is equal to 10 to the power of 16 into e to the power of minus 2000 by T. Now they are saying that what temperature K1 should be equal to K2. So I can write K1 is equal to K2. What should be its temperature? So I can write that 10 to the power of 15 into e to the power of 1000 by T should be equal to 10 to the power of 16 into e to the power of minus 1000, right? So minus 2000 by T. Okay, so now what I can do, I can divide this one here. So I'll get e to the power of minus 1000 by T by e to the power of minus 2000 by T. That will be equal to 10 to the power of 16 by 10 to the power of 15. Okay, now what happens if I solve this one? I'll get e to the power of 1000 by T is equal to 10. Okay, now to solve for T, what I can do is I can take ln on both sides. So I'll get 1000 by T is equal to ln of 10. Now to convert it into log, I can multiply 10 here, multiply 2.303. So I'll do 2.303 log of 10. Now I know log 10 value is 1, right? Then T will be equal to what? Then T will be equal to 1000 by 2.303. Okay, the correct answer for this question will be your option number C. Getting? Very easy question, little trick question. Okay, now coming to the next question here. the rate constant of a reaction is given by K is equal to Pz e to the power of Ea by RT under the standard notation. In order to speed up the reaction, which of the following factors has to be decreased? Now we have just studied that if activation energy decreases, the rate constant will increase, right? So that is why. So now if you see, which of the following, in order to speed up the reaction, to increase the speed of the reaction, which factors should be decreased? Both Z and T. But if you decrease temperature, we have just read that for every, when you increase the temperature, the reaction will increase. But if I decrease the temperature, reaction will also decrease. Now you can see K is directly proportional to Z. If you decrease Z, K will also decrease. So that this is not the answer. But Ea, it will work because we have just discussed that K is proportional to 1 by e to the power of Ea by RT. If temperature is decreasing, this fraction will decrease, the whole e to the power of something will decrease, then K will increase. The correct answer for this question will be option number B. Okay, very simple question. Next, coming to question number 3, that is from 2018, the temperature coefficient of a reaction is 2. Okay, when the temperature increases from 30 to 90 degrees Celsius, the rate of the reaction increases by. Okay, so see now, temperature coefficient is 2 means it tells that for every 10 degree rise in temperature, the rate constant becomes double. Now from 30 to 90, 30 to 40, 40 to 50, 50 to 60, then 60 to 70, 70 to 80, then 80 to 90. So how many times we have increased? 1, 2, 3, 4, 5, 6, right? So 2 to the power of 6 you need to do, right? So how much will get? 2 to the 4, to the 8, to the 16, to the 32, 32 to the 64, right? So the rate constant will increase by 64 times. Correct answer for this question will be option number D. Okay. Now coming to question number 4, which is a wrong statement, 2019 question. Rate constant K is equal to Arrhenius constant A if activation energy is 0. Let us check that. What will happen? K is equal to A into e to the power of Ea by RT. Now if activation energy is 0, then it is e to the power of 0, that is 1. Then I can say K is equal to A. So that is what they are saying rate constant K is equal to Arrhenius constant if A is equal to 0. So this is a correct statement. Next, e to the power of minus Ea by RT gives the fraction of reactant molecules that are activated at this given temperature. Yes, I just discussed that. E to the power of minus Ea by RT tells you the number or fraction of molecules that has energy or greater than or equal to activation energy. So this statement is also correct. Now ln K versus 1 by 2 is a straight line. This statement is also correct. We have just seen the graph. Presence of catalyst will not alter the value of Ea. This is wrong. Presence of catalyst will do what? Will lower the value of Ea, right? So this is a wrong statement. Correct answer for this question will be option number D. Okay. Now coming to question number 5. Higher order is greater than 3. Reactions are rare due to. Okay. So they are saying that order reactions more than 3 is probably very less reactions are found in that. Why? That can be the reason for that. What can be the reason for that? So shifting of equilibrium towards reactant during elastic collision, not like this. Loss of active species on collision, not like this. Low probability of simultaneous collisions of all the reacting species. Okay, this is the correct answer. See, generally 2 reactants can react, 2 to 3 reactants can collide with proper orientation and with proper energy. More than 3 reactants colliding with proper energy and proper orientation is very low. The probability is very low. That is why we cannot find the order greater than 3. Okay, the correct answer for this question is option number C. Okay. So yes, now let us do a small recap here. This graph you can see for Arrhenius equation, K is equal to A to the power of minus Ea by RT. This graph is for this equation. Then ln K, if you take 2 sides, will get this graph. Then for 2 different temperatures, I have this equation. Okay, ln K to log K2 by K1 is equal to Ea by 2.303 R1 by T1 minus 1 by T2. This formula is very, very important. Please remember this formula, note down. Okay, very important one. Okay. Yes, so students, we have come to the end of this chapter, Chemical Kinetics, which is a very important and high weightage topic. We have completed all the concepts starting from effect of concentration, effect of temperature, effect of catalyst, collision theory. Each and every concept has been completed with PYQs and with practice questions. So I hope all of you would have got some confidence regarding this chapter. And if you have any doubt in any of these concepts, please comment down. I will definitely address it. Okay, so yes, if you are liking this series, if this series is helping you to get motivated to understand the concepts of chemistry in a better way, then please subscribe the channel and continue this series. We are going to cover every chapter of chemistry and we'll be doing a lot of practice questions so that we can hit that perfect 60 out of 60 score together. Okay, so yes, now I hope all of you have, and please remember, keep making your notes. Okay, and every day with the class you can make notes and keep them for revision. Okay, so yes, now that's all for this video, and let's meet in the next session or next episode of this series where we are going to start the chapter D and F block elements. Okay, so yes, please comment down how did you like this series, whether it was good or not, whether it was helpful or not. Please give your feedback for this. Thank you once again and all the very best for your preparation. See you in the next episode very soon.